Welcome to the Thursday and Friday video lesson. So we started our warm-up thinking back to what are those electrons on the very far outside of our atom called? Most of you guys were right. It was valence. I was kind of hoping more of you guys wouldn't remember and I might get some creative answers, but you know what? I'm happy. You guys did really well, so good job. And then I asked you guys to reflect on the quarter. Now, in normal years, when we're doing in-person learning, I usually ask you at the end of every week. But since I've only seen you twice per week this year, I wanted to make sure you had different warm-ups each time. So now this is our last chance for the quarter. I'd like to know, how was your quarter in chemistry? How do you feel on a scale of 1 to 10? Now, I've heard rumors, unconfirmed, that you guys have a life outside of honors chemistry. I don't really believe it, but it might be true. So how was your life outside of honors chemistry in these past 9 weeks? At home, other classes, just kind of overall. And then it's always good to reflect, what have we learned? So what's one thing that's going to stick with you? What's one thing you learned in these last 9 weeks that's really going to stick with you for life? So once we finished our warm-up, we then went and finished our Unit 3 notes because we had like 3 more slides. And then we went on to talk about valence electrons and your homework assignment with that. And we went over the periodic families. So your homework, your first assignment of marking period 2 is the Bohr model PDF, is to finish your Bohr model PDF. You've already started it. You've done more than half of the work. You did the hard part of the work. Now you just need to finish that table at the bottom. So slide 23. So my metals tend to lose electrons to become stable. So in order to be stable, I want to have a filled valence shell. I want to have 8 electrons on my outside ring. So for my metals, I have 2 choices. So here's my sodium. It has 1 valence electron. So if I want to have 8 electrons on my outside, my sodium has 2 choices. It can go through all the work and get another 7. Wait a second, I can do this easier. 1, 2, 3, 4, 5, 6, 7. So my sodium can go around and find 7 more electrons to add to its outside ring. Or it has another option. It can just get rid of that guy. Because if I get rid of that guy, then I have 1, 2, 3, 4, 5, 6, 7, 8 electrons on my outermost ring. So my sodium has 2 choices: gain 7 or lose 1. Atoms are lazy. They will do the path of least resistance. So it's a lot easier to lose 1 than to gain 7. Here my magnesium has 2 valence, so it can gain 6 to get to an 8, or it can lose 2 to get back down to its 8. So they're low ionization energy, which means it's really easy to get rid of those valence electrons, makes it easier to lose an electron and be more reactive. It's kind of, as I go down a group, my reactivity increases because my ionization energy decreases. Did you know that when teachers use food-based examples, students remember it better? I kind of like to think of ionization energy as the price. So we all know McDonald's. When you think of McDonald's, I think we all think of the same thing: a Big Mac. That's what McDonald's is famous for. But McDonald's also sells hamburgers and cheeseburgers. McDonald's sells more hamburgers and cheeseburgers than Big Macs because part of the reason is because they're so much cheaper. They might be known for their Big Mac, but if I only have so much money and I need to go and buy, if I'm going to McDonald's every day and I only have so much money, I'm not going to buy a Big Mac every day. I'm going to buy a lot more cheeseburgers and hamburgers because they're about $1 or less. I don't actually know how much they cost right now. More so than those Big Macs that cost $3 or more. So as the price is lower, it's easier to do. It's going to happen more often. And then as I go across my period, my metal reactivity decreases because my ionization energy increases. So those are my Big Macs. I still like Big Macs. Big Macs are still delicious. I probably shouldn't say that because, that's not healthy. Maybe that's why I'm not teaching nutrition this year. They cost more money. McDonald's sells a lot of Big Macs. Where's my active slate? Right underneath my keyboard. They sell a lot of Big Macs every year, every day, but they cost more, so they aren't selling their Big Macs nearly as often as they're selling their cheeseburgers and hamburgers. So here I've got sodium and magnesium. Sodium is going to be more reactive than magnesium because it only has, that one valence to get rid of to react. Whereas magnesium needs to find someone to take off both of those electrons. It has 2 burgers to sell. So it's going to be harder to sell those 2 burgers than that 1 burger. Also, my sodium electron is also on the 3rd energy ring, just like magnesium. But my sodium is bigger, so that electron is further from the nucleus. This one is closer, this one is held tighter. But then when it gets to my strontium, again, I have to get rid of these 2 electrons like my magnesium. But those electrons are also less well held than sodium. Sodium is going to be slightly more reactive than strontium, that's just a thing. But my strontium is a lot more reactive than my magnesium. And then, I want to make sure my chat's open. Then also slide number 23, my nonmetals tend to gain electrons to become more stable. So my nitrogen here has 5 valence electrons. So in order to get 8, I can gain 3. 1, 2, 3. And now I have 8 on my outside. Or I can lose 5. 1, 2, 3, 4, 5 to have a filled valence shell. Now I know it only has 2, but since the first energy level can only hold 2, that's considered a full valence. For everyone else, 8 is a full shell. Which is why I like to lie and say 2 and then everyone else gets 8. And then just not mention that it gets more complex. So what's easier? What's the smaller number? 5 or 3, everyone? If you're on camera, show me fingers. 5 or 3? Exactly. 3. So it's a lot easier for it to gain 3 than to lose 5. And here's my fluorine. It has 6, so it only needs to gain 1. And then here's my bromine. It has 7. It only needs to gain 1. I think I said 6 there. That's 7. So increased electronegativity means it's easier to attract electrons and be more reactive. So as I go down a group, my non-metal reactivity decreases because electronegativity decreases. So here's my fluorine and here's my bromine. They both have 7 valence electrons. They just need that one more valence electron. They are both desperate to get that one more electron. But fluorine, those valence electrons are a lot closer. So they feel the pull from that nucleus a lot stronger than these guys do for my bromine. So fluorine is going to be much more attractive to any unsupervised electrons or loosely held electrons it comes across. My nonmetals are wicked. They will they will cheat, lie, and steal to get their valence electrons. And then as I go across a period, my nonmetal reactivity increases because the electronegativity increases. So as I go from nitrogen to fluorine, my fluorine is more reactive than my nitrogen, partially because I have such a stronger pull. Actually, I should have made my fluorine a little bit smaller than the nitrogen. Whoops. There we go. So see, my fluorine is smaller than my nitrogen. So that effective nuclear charge pulls it in stronger than these electrons are for nitrogen. I also like to think of it like you're trying to complete a set. So Burger King does those special glasses all the time. Let's say Burger King does a special Frozen 2 promotion. There's 8 limited edition Frozen 2 glasses. If you have 5 out of the 8, it'd be kind of nice if you could, get those last 3. But if you have 7 of those 8, and you don't even like Frozen 2, but if you have 7 out of the 8, you kind of want to complete that set. You might not care about Frozen. You might not care about having nice glassware in your cupboard, but you almost have that complete set. Maybe you want it for bragging. Maybe you want to sell the complete set on eBay. You really want that one last glassware. Whereas if you're something like sodium, so out of the 8 Frozen 2 glasses, sodium gets 1. Well, do you really want just 1 out of the 8? No, people are going to think you don't have much dedication. They're going to think you don't have grit. You got 1 and you gave up. Even if it's Olaf, even if it's your favorite. So you might as well just sell it on eBay. Get some money. Get rid of it. You don't need it. It's just taking up space. It's not the full set. Just get rid of it. That's the other way I like to think about it. So then we go to slide 22. How likely an element is to react with other elements in order to gain an octet. Which, let me write in parentheses. Not parentheses that tiny. 8 valence electrons. So they want to either react and get rid of their valence electrons if they're a metal, or they want to react and gain valence electrons if they're nonmetals. So the best element at getting rid of its electrons is francium. This is our largest of all of the atoms. It holds on to its valence electrons the weakest, and it only has to get rid of 1 valence and done. For my nonmetals, my most reactive nonmetal is fluorine. Fluorine is my smallest non-noble gas element. It has my strongest effective nuclear charge at a +7. It's holding those electrons super close, and it just needs 1 more. It needs 1 more electron, and it's got the full set. So fluorine is my most reactive nonmetal. It was kind of confused with oxygen for being the most reactive, but it does something called oxidizing. If you've ever heard of oxidizers or seen a warning that says, warning, this compound is a strong oxidizer, that means it's really good at stealing electrons off of other compounds. If any of you guys have worked as a lifeguard, you might have seen it on those chlorine bottles at your pool. And then my most reactive of the noble gases is none. My noble gases do not react because they have their filled valence shell. They have those 8 valence electrons, or for hydrogen, it has its 2. So they don't need to react. They have their full 8 valence electrons, so they don't care. Now, in the last 20 years or so, we have managed to make a compound with like xenon. I'll give you guys 2 shakes and a whistle to finish that up. Why do I have Task Manager open? Wonder how that happened. All right, next on our to-do list is that homework. So here, let me change my share. Past lessons. Yep, that's the page I was on. So in your modules, you know, I'm going to move this up. Let me rearrange this slightly. You have homework, finish Bohr model diagrams, and you've already done the harder, longer part of this. So I did say you should save this. You probably saved and submitted this. Oh, you know what? I can put a link to the old assignment. Edit. For a new blank copy. And you should be able to find and download your old copy here. So let me make this a link. Assignments. Oh golly, this was CW. Bohr models in the periodic table. There we go. So if you can't find yours, if you never submitted it, if it didn't save, you can get a blank copy here that will download the PDF. Ha ha ha. That is a good question. And I'm going to let you marinate with that question. And thank you for that update. So this will download a PDF. This should take you to the old Kami assignment. I would download it to your computer, and then you guys should have this little purple circle with a K. That's the Kami plugin. You can upload files, edit it, and then download it. Let me change my share again. So what you're doing here is that bottom table. Because I said before, all I wanted you to worry about was putting those electron dots. And we talked about how many valence. Oh, hey, look, there goes the data for there. Now, I want you to figure out how many will they lose or will they gain. So they want to lose or gain to have that full shell. I kind of mentioned a few of these already in our notes. And in our Unit 1 notes, we talked about how you lose and gain. If you lose electrons, you get a positive charge because electrons are like homework. If you gain electrons, it's negative because electrons are like homework. So I mentioned my sodium has that one valence. If it gets rid of that one valence, so that would be one valence lost, its charge would be +1. Because if you came into class and I told you you guys have 20 homework problems to do tonight, and at the end of class I said, never mind, you have 19 problems to do, you'd be happy. You have one less assignment to do. That's a +1 happiness. So when you lose electrons, you get a positive charge. But then I was talking about fluorine. It desperately wants that one more electron become 8. So that's like coming to class and me saying, you have no homework today. And then me saying, no, you do have an assignment. So that would be a -1. And I will let you do them, figure out the rest. And I'm probably going to mention the answer to that one question in the lab in the chat in a bit. So that is your homework. You're just going to upload your new PDF or an image file or whatever. I'm flexible. And I am not going to take the time in class today to go through this presentation. And let me change my share again because it's just so much fun to mess with you like that. Share. When you open it up, it's going to make a copy of this in your Google Drive. When you go through this, what you want to do is you want to press share. Nope, that's not it. Sorry, that's a lie. I shouldn't lie to students. Sorry. Go to the present mode. And then when you click on things like definition, it'll show you the definition here. And then you can go to here, here. You can bounce around. And then go to the periodic table, and you can look at atoms grouped by valence electrons and other elements. So this is a reading assignment for this weekend. We already kind of know this, and what I want you to know, what I want you to be able to reference for notes, I'm going to be giving to you in a guided notes packet. But this is here to help you out with that valence electron homework. We'll put this in presentation. So there's nothing to fill out for the periodic table family's notes. So group 1, so that first column, these are my alkali metals. These are all incredibly reactive. They will catch fire if you put them in water. Some will actually explode. Now they're called alkali because they make an alkali solution. Most of us have heard of acids. A base or an alkaline solution is the opposite of acid. Acid and base, acid and alkali. So they dissolve and make the opposite of acid with water. They're all very soft. You can cut all of these with knives. They're all silvery, very soft, and they're solid. And as you go down, they get more and more reactive, and they all have that one valence electron. So here's what they all look like. Almost all of my metals are silvery, silver and shiny. And notice sodium, potassium, rubidium, and cesium. These are all, if you look closely enough, being kept in containers with a liquid. They actually have to be stored under oil, or else they'll react with the oxygen in the air. Let me undo this. And fun fact, it is illegal for me as a teacher to keep samples of these in our classroom because they are so reactive. Now I have 2 videos I'd like to share. So let me change my sharing settings to optimize. This is one of my favorite videos that we share. Now what they're going to do is they're going to cut this metal with a knife, and I want you to look and see it starts shiny. Look how fast it goes from shiny to dull. It's kind of pixelated, but you can still kind of tell.
There are 6 alkali metals: lithium, sodium, potassium, rubidium, cesium, and francium. They're all soft metals which can be cut with a knife. In air, the elements quickly become coated with compounds that form on the metal's surface. Here, for example, is lithium. When we slice it, you can see the metallic luster, but the black coating quickly reappears. Sodium is kept under oil to prevent reaction with air. Again, when we cut it, the metal's surface can be seen. But this time, corrosion occurs even more quickly. With the next alkali metal, potassium, the corrosion in air is so quick that it's hard to see the metallic luster at all. As we go down the group, the elements seem to react more quickly with air. Now let's see another reaction of the alkali metals, the reaction with water. We'll start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. All the alkali metals react with water in the same way. Let's see an equation for the reaction. Hydrogen gas is produced, and the metal dissolves to give an aqueous cation with a single positive charge. Now for potassium. This time you'll see a flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catches fire. It burns with a lilac flame. The next element is rubidium. This time we put a safety screen between us and the reaction. You can see that things gradually become more terrifying as we go down the group. Let's try cesium, our 5th alkali metal.
And then we have the alkaline earth metals. So this is group 2. Oh yeah, so if there was anything alive in that lake, it's dead. They mentioned it was already an alkali lake, and I actually started looking up the name of that lake because I'm kind of curious to see if there's still lasting results. Um, so yeah, anything in that lake, fish and most things don't like acidic things. They also don't like basic things. They like neutral water. That's what we like to drink. Please, please, no one in my class ever fall for one of those alkaline water scams. They're all scams. If it's alkaline water, it's going to taste like soap, and it's not good for you. If it doesn't taste like soap, it's neutral, and you paid money for something that you can get from your faucet. Sorry. Anyway, most fish don't like it because alkaline solutions are very good at dissolving biological proteins. So if there was anything alive in that lake, it was dead after that. And it's probably still very basic from that, unless they do get a lot of acid rain in the Southwest. So it could have been balanced out by now, but I don't think they get that much acid rain. So group 2, now we had 1 valence electron. These guys have 2 valence electrons. They're also very reactive as far as metals are concerned, but not as reactive. They won't explode with water, but if you put them in test tubes with water, they will bubble. So as you go down, they get bigger. So down here, sorry, I used to have a video that had beryllium, magnesium, calcium, and strontium all in water. The strontium bubbled a lot. The beryllium and magnesium bubbled a little bit, and the calcium bubbled slightly more than the strontium. It wasn't very exciting, and I can't find the video, so you're not missing out on too much. But again, these are all solid. They're all silver. They're not as soft as group 1, but like magnesium, I always have a ribbon of that in my classroom in my drawer, and I easily cut that with scissors whenever I feel like burning some for a demo. When I have half a reason to burn something in class, it's right there so I can burn it. And the barium and strontium are being kept in oil just to keep them from reacting with the air. Again, they won't react quite as bad as the alkali, but also barium is very poisonous. And then in the middle was the transition metals. This is the group that I usually skip whenever we're doing trends because they buck some of those trends. They have 1 and 2 valence electrons, but sometimes they feel like having 3 or 4. It's a bit weird. The best thing for you guys to think of it right now, who are curious why is that, it's like a chipmunk. They've got those extra pockets where they can store extra things in. They're all solid metallic, and they don't react too much. And this is where we get all the really pretty colors in the world, is mostly thanks to our transition metals. So copper is a reddish metal, but it's responsible for most of our pretty blue compounds that we see in nature. And then because these aren't very reactive, that's where we get our coinage metals, gold, silver, copper, also for jewelry. If you want to make a necklace, you want a necklace that's going to stay that necklace, that shape, for many, many years. If you make a gold necklace, it'll stay looking that same way. It might tarnish a bit on the outside, but it'll stay in that same general shape for thousands of years. If you were to make a necklace out of potassium, well, then I hope you aren't outside when it rains one day, because these are very reactive, but my transition metals are pretty stable. That's also why a lot of these, silver, copper, gold, nickel, have been known since ancient times because they don't really want to react with other compounds. They just want to be with themselves, really. And so since they're so happy to just be with themselves and not react with others, you can find gold nuggets. You can find veins of silver in rocks. So because they don't react as much, they're easier to find by themselves as well. Then we get over to the right side. So now some people call it the boron group. This isn't really a family. Transition metals was a family. But here we all have 3 valence electrons. So you can lose 3 or gain 5. So aluminum, gallium, indium, and thallium all want to lose those 3 valence electrons. They're metals. There's nothing that weird about that. Boron is our first metalloid. Metalloids are strange. They can gain or lose valence electrons. Boron is a bit of an exception to the octet rule. It actually is happy with 6. So boron is actually right in the middle of its valence shell. It can lose 3, or it can gain 3 to be happy, or it can gain 5. Metalloids are weird. Then I have 4 valence electrons. And so this was a question that someone had in the chat, and now I'm going to address it. If you have 4 valence electrons, really you can gain or lose, because there's nothing is more or less easy for that. Carbon has those 4 valence electrons. It would rather gain. It's rather electronegative. It's really good at bringing in new electrons, so carbon tends to really only gain 4 new electrons. But even then, it doesn't really make an ion. Silicon and germanium, they could gain 4 electrons, but they're also big enough that they wouldn't mind losing them. So they're metalloids. And then tin and lead, it's actually easier for them to lose their 4 than to gain 4 because they're so big. They're metals. And that's kind of why we categorize these the way that they are. Because they're so big, they're not going to want to gain any. Then my nitrogens. So these guys all have 5 valence. So nitrogen and phosphorus, it's no question to them. They want to gain 3 valence electrons. Arsenic and antimony, they could go either way. They are metalloids. And then bismuth is a metal. It's so large, it would rather lose 5 electrons than gain 3. And I just like to show how pretty bismuth is. If you've ever taken Pepto-Bismol, this is part of that active ingredient is the bismuth. That's how it got its name, Pepto-Bismol. What you doing with all that element 83? None of your bismuth. Good at none of your business. And the double and triple bonds is interesting. We'll come back to that later. But these are good notes to have. Oxygen group is our last fake family. It's kind of a family, but no one really counts oxygen, nitrogen, carbon, or boron as families. So now we all have 6 valence electrons. So oxygen through selenium. Selenium, a vital nutrient you get from chicken. They all just want to gain 2. But tellurium and polonium, they're metalloids. They could do either. They could gain 2 or lose 6. Now the next actual family. So normally when we do families, we just talk about the alkali, the alkaline, transition, and then we skip to the halogens. So this is an important group. My halogens are very reactive. Fluorine, chlorine, bromine, iodine, and acetane. Acetane, which was only really confirmed to be existent in the last couple decades because its half-life is about 30 minutes. So if I make 5 grams of acetane after 30 minutes, I only have 2.5. So it's actually, no way, I think its half-life is 18 minutes. It's even shorter than that. There's less than a pound of acetane in the world at any given time. This is why we have a hole in the ozone, because my halogens are very reactive. They can't exist by themselves. I can't have a single atom of fluorine or a single atom of chlorine, bromine, iodine. They have to be bonded with someone. So if you have pure fluorine, you have fluorine bonded to another fluorine. If you have pure chlorine, you have chlorine bonded to another chlorine. In the upper atmosphere, we have chlorine and fluorine compounds. What happens is that solar rays come by and kind of slice those atoms apart in those compounds. And then you have an atomic fluorine, and it can't stand to be by itself. It has to make a new friend. It has to find someone to connect with. And so what happens is it finds oxygen molecules. Sorry, not oxygen. Ozone molecules, which have 3 oxygens. And it says, give me one of your oxygens. And it will steal an oxygen off of ozone. That happens enough, and now there's an ozone layer hole. So those chlorine and fluorine, they will steal electrons, they will steal atoms from other compounds. That's why chlorine, bromine, and iodine are used so often as disinfectants, because they're so good at disrupting molecules. If you're a single cell bacteria or a virus, you don't have that many molecules. You don't have that many compounds. So if just a few of them are compromised, a bacteria or a virus will die. If you count viruses living, viruses aren't really living. That's why we use chlorine in pools. It's very good at killing stuff. It's very good at taking off electrons and disrupting molecules. And then our last real family that we should care about is the noble gases. These all have the valence shell of 8. It's what everyone wants to be. They don't react because they are perfectly content. It's only lately, in the last couple decades, I keep saying this really fun fact, that we were able to get xenon and I think krypton to bond with other elements by having it, distracting. Hey, look over there. And while I was looking over there, we attached another atom to it. And they all exist as gases because they don't need to bond. They don't need to make compounds, so they never make solid compounds. They just exist by themselves as an atom, as a gas. Then lanthanides. This is good to know just because it's that top row of those 2 rows that sit underneath. They're all very radioactive, shiny. There's really nothing to say about them. They're pretty boring. Acinides are the bottom row. They are also not used for that much, but after uranium, so after 92, these are all man-made. We have our nuclear fuels here with plutonium and uranium. Fun fact, plutonium is Pu rather than Pl because Charles Seaborg, I forget his first name, Dr. Seaborg thought it would be hilarious that for decades, centuries after he died, kids would be talking about Pu, the stinky element. That is a true story. I am not making that up. There's a dad joke on the periodic table. I love that man for that. And americium we use in, what's that called? Oh, smoke detectors. And so they have a few uses, usually for detectors and stuff. But they're all man-made after uranium. So that's what we went over in class today. Don't forget, the deadline for quarter 1 work is Sunday at midnight. So the real firm deadline, I am not accepting any work after Sunday night at midnight. Your periodic trends reasoning activity and your periodic app screenshot are both due on Friday, the 6th. After that, then it is late, so you still have a little bit of time, hopefully, to get those in, but a full stop on all work Sunday at midnight. And that's it, I guess. Good luck, guys. Hope everyone had a good first quarter, and stay safe and make good choices, everyone.